All right, now what we're going to look at is what happens when x is large. And there's some terminology for this. When we say that when x is a very large number, and you plug in x into these two functions, and no matter and for not just any very large number, but for all very large numbers past a certain point, if the g of x is always greater than f of x for all very large values of x, we say g dominates f. So, let's look at some examples of this. Let's see which function dominates. So, with a here, we're going to plug in, let's start with some small values of x, and then we'll see what happens. Oops. So if you plug in like 1 or 2, let's see, f of 1 is going to be 3 times 1 squared, which is 3. G of 1 is just going to be 1 times 1 times 1, which is just 1. Okay, so far it looks like f of x is bigger. If you plug in 2, f of x, let's look at f of 2 over here, is going to be 3 times 2 squared, which is 2 squared is 4, so this is 3 times 4, which is 12. G of x is going to be, g of 2, is going to be 2 to the power 3. And 2 times 2 times 2 comes out to be 8. So, okay, so it looks like f of 2 is still bigger. And then when you plug in 3, we'll see what happens. G of 3, or I guess I should do f of 3 first. F of 3 is going to be 3 times 3 squared, which is going to be 3 times 9, which is 27. And G of 3 is going to be 3 to the power 3, which is the same thing, also 27. So at this point they're the same. And then if you plug in 4, well, f of 4 will be 3 times 4 squared, which is 3 times 16, which comes out to be 48. G of 4 here will be 4 to the power 3, which, just looking at these, they're kind of the same. They both have 3 numbers getting multiplied, but now suddenly G of 4 has just 3 copies of 4, which is going to be bigger. So 4 times 4 times 4, which is bigger than 3 times 4 times 4. And indeed, this comes out to be 64. And as you go up here, if we're going to do f of 5 and g of 5, f of 5 is going to be 3 times 5 squared, whereas g of 5 is going to be 5 to the power 3. So 5 times 5 times 5 is going to be bigger than 3 times 5 times 5. 1 is going to be 125. G of 5 is 125. And 3 times 5 times 5 is 75. So you can see here that plugging in bigger values of x, anything bigger than 3, is going to make it so that one of the factors in x cubed is bigger. So this one definitely dominates. Any bigger number that we plugged in is going to make g of x bigger too. And a similar thing is happening with part B here. Let's see. This is what if the problem was just that 3 was too small? We had 3x squared versus x cubed. What if we make it 10x squared? I'm going to make a similar table here. Let's look at some values of x and p of x and q of x. And sure, if we start with something like 2, or let's plug in 1 actually. If you do x equals 1, 10 times 1 times 1 is going to be 10. Q of 1 is going to be 1. So p of x is way bigger when you plug in a number like that. If you plug in x equals 2, P of x is going to be 10 times 4, which is 40. Q of 2 is going to be 8. So 40 is way bigger than 8 so far. But what we care about is the really large values of x. So I'm going to see what happens if we plug in 10 or 11 here. So if you plug in x equals 10, P of 10 is going to be 10 times 10 squared, which is 10 times 100, which is 1,000. If you do Q of 10, you're doing 10 cubed, which really just means 10 times 10 times 10. It's the same thing. It's 1,000. And then what if you plug in 11? Well, once you plug in 11, P of 11 is going to be 10 times 11 squared, which is, in other words, 10 times 11 times 11. And when you do Q of 11, that's going to be 11 cubed, which is 11 times 11 times 11, which is going to be bigger. And I need a calculator real quick to work this out. So yeah, 11 to the power 3 is 1,331. And 10 times 11 squared is going to come out to be 1,210. All right. Okay, so you can see that having the bigger power of x, the bigger exponent, is what's really mattering here and making it so that the function q of x dominates the function p of x. Even if this number was really big, even if you had like 1,000 here, all you'd have to do is plug in x equals 1,000, and the q of x would catch up. So if x is very large, this is gonna dominate. Okay, with C, it's a little harder to do the arithmetic with this one, so I'd like to try graphing it on Desmos. So I'm going to open my browser, go to desmos.com, and so we're graphing y equals 100 times x cubed. That's a function that's going to get really big really fast. Okay, so there it is, shooting right off the top of the graph, because it's so steep you can't even see it much there. And then the other one is y equals 0.1, that's a pretty small number, times x to the power 2.5. This question I just realized is boring. I think I meant to make it different. Okay, so all right, as it is, as this question is, the k is smaller and the p is smaller. The exponent is smaller here too. So the second function is definitely going to be smaller. And you can see that here. But what I want to do is zoom out a bit. Try to zoom in the y direction here. There we go. And you can see even when you scrunch it down this far, the red one is going off the top. So yeah, so this one is always going to dominate. I think what I meant to do with this question is, I'm going to make this be part D, is what if you had these mixed up? Let's make it a little bit more interesting. So if you had f of x equals 0.1 x to the third power versus 100, let's call it g of x, is 100 times x to the 2.5. Okay, so if the one starts with a much smaller coefficient, but has a slightly bigger exponent. Let's see what happens. Okay, so we're going to have 0.1 x to the third power, and then 100 times x to the power 2.5. All right, so what you can see here is that at first, the 100 x to the 2.5 is much bigger because the 100 is way bigger. And like on this scale, the 0.1 x to the third power is sitting right on like the x-axis there. And what I want to do is zoom out a bit, see what ends up happening when we start plugging in bigger and bigger values of x, like x equals 80, 80 or 100 here. Is suddenly it looks like the red one, the one with the x to the power 3 in it, starts curving up a bit. And if we zoom out and farther, we'll see that happening some more. So here we're plugging in numbers like x equals 500 or 1,000. It looks like even plugging in 1,000, the red one is still smaller. The one with the larger exponent, but the smaller coefficient. But I'm going to keep zooming out. Oh, it looks like on this scale, the red one is catching up a little bit. My computer's a little stuck. All right, here we go. We'll keep zooming out until we're plugging in numbers like 100,000. Not quite big enough yet. Oh, look, on this scale, it looks like it's getting closer. Oh, wait, what's happening here? Around this point, this point, it looks like they meet at, they intersect when x is 1 million. So if you plug in x equals 1 million into this, then the x to the power 3 starts getting bigger. And the 0.1 in front doesn't matter as much. And sure enough, if you keep zooming out here, you can see on this scale, looking like this is 2 million, 4 million, 6 million, and so on, then at this scale, you can see the red one is clearly dominating. In between these two, the one with the higher exponent wins. So yeah, so for very large values of x, the bigger exponent wins. Okay, so let's do a few examples now where we try to write a power function, or one example where we try to write a power function. You've got some exercises like this too. So let's say that if y is proportional to x squared and y equals 20 when x equals 3. So what does that y is proportional to x squared mean? Well, back from chapter 1, I think we talked about proportionality. We'd say y is proportional to x. What that means is y equals k times x to the p. Wait, no, just k times x. For some constant k. But if now we're saying y is proportional to x squared, then this should be x squared there. So we want a function that looks like this. Y equals some number times x squared. But we don't know what the k is. So we don't really have a power function yet. But we can find what the k is using this fact that y is 20 when x is 3. So I'm going to plug in 20 for the y. That's going to be equal to k times x, 3 to the power 2. And 3 to the power 2 is just 9. So 20 is equal to k times 9. So to find the value of k that works for x equals 3 and y equals 20, we just need to divide both sides by 9, and you get k is equal to 20/9. So the power function that we want is going to be y equals 20/9 times x squared. Alright, so yeah, again, y is proportional to x squared here because it's written as y equals a number times x squared. Okay, let's look at example 5 here. Let's see, we got two graphs here. We want to know which one is y equals x to the negative 1 and which one is y equals x to the negative 3. So, just by looking at these graphs. Well, what I want to do is think about, well, first of all, let's remember, what does x to the negative 1 mean? In general, a to the negative n, just remember from g.1, is 1 over a to the n. And if you don't know what I'm talking about, you probably need to go back and do the g.1 notes. So this y equals x to the negative 1, that's another way of saying y equals 1 over x to the 1, or just 1 over x. And this one is the same thing as saying y equals 1 over x to the power 3. Okay, so that's what these are written as fractions. And let's see how does the 1 and the 3 affect the shape of the graph. And just to figure that out, what I want to do is just plug in some numbers. Like, let's plug in x equals, let's try 0.5 and 1 and 2. And we'll see what happens to 1 over x there, and also see what happens to 1 over x to the power 3. Okay, so let's start with the easiest one to do the arithmetic with here in the middle. If you have x equals 1, well, 1 divided by 1 is 1. And 1, if you replace this x with 1 here, 1 divided by 1 to the power 3, that just means 1 divided by 1 times 1 times 1, which is still just 1 over 1. It's 1. Okay, so we got that. Then let's do this a little backwards. Let's plug in x equals 2 first. If this x is 2, then we're just going to have 1 over 2, which is 0.5. Here, if you do 1 over 2 to the power 3, that's 1 over 2 times 2 times 2, that means 1/8, 1 over 8, which is 0.125 if you divide that out. Alright, what happens if you do plug in x equals 0.5? Well, 1 divided by 0.5, 0.5, is 2, because like 0.5 goes into 1 2 times, so that's going to be 2. And if you do 1 divided by 0.5 to the power 3, well, 0.5 to the power 3 is 0.125. Every time you do like 0.5 times 0.5 times 0.5, it gets cut in half every time there's another 0.5. So it ends up being pretty small in the denominator. And that turns out to be 8. Alright, so what this is saying is that they cross at x equals 1, which you could see in the graph anyways. But if you plug in a number bigger than 1, like x equals 2 here, then what happens is they're both results, both y coordinates are less than 1, but only one of them is much less than 1, the 1 over x cubed. So it gets a lot closer to 0 there than this one does at x equals 2. And if you plug in something less than 1, like 0.5, which is about here. Whoops. You can see what happens to these coordinates. This one gives you 2 for the y-coordinate. The other one gives you 8, which is way up here. So yeah, the dotted line one must be 1 over x to the third, or y equals x to the negative third. And the solid line one must be y equals x to the negative 1. So they have some things in common. They both have these, what you call asymptotes here. Like as x gets really big, these both of the y-coordinates in each graph get close to 0. And if x likewise is close to 0, then the y-coordinates get really big. But the difference is that if x is a bigger number, something bigger than 1, then the one with the bigger negative power of x, or the bigger exponent in the denominator, ends up getting closer to 0. So this value of y gets close to 0 faster than the x to the negative 1 does. All right, so this is some sort of, there's some kind of advanced sort of concepts here. When you go on to take pre-calculus and calculus, you're going to look at this in a lot more detail. So you can think of this as sort of a preview to gain some skills that will help you in calculus. And looking at graphs from this perspective by like making a table and seeing what happens to the values is a really important way for analyzing graphs in general. So that's the main thing I want you to get out of this. If you want to know what a graph is shaped like, plug in some numbers and see where those points end up. And that's the end of this one. Up next you have some exercises. So of course you're going to do those yourself, or try to do them at least. I'll show you how I would do them, and so you can check your answers in the next video.